Today we have Sam and Trevor joining us, and many of you will be familiar with Samuel. He's a host of many of the reading groups in the past, so for the regular attendees, he's a familiar face, and he's a PhD student at the University of Edinburgh, and he's advised by David Abel and Chris Lucas. And before he did his PhD, he did aeronautics at Imperial College London, and he spent 3 years in London working in the robotics industry. And today, Sam's joining us from Beijing, where he's doing an internship at Microsoft Research, and he's investigating world models and generative models and how we can use these for our training purposes and how they can act as neural simulators. And he's broadly interested in the interactions that arise when learning systems shape their own sort of training distributions. And this is a key characteristic in online RL settings. And I think today we'll actually see some very interesting things about this as well. In the presentation, at least from the paper, there's some interesting findings there. And Trevor is also a PhD student at the University of Edinburgh, and he's a member of the Bayesian and Neural Systems Lab, supervised by Amos Storkey. And his research focuses on many pathways on how we can get reinforcement learning into the real world. And this includes sort of offline settings and off-policy methods, as well as representation learning in high-dimensional observation spaces, and also model-based methods. So I guess those are the intros, and I'll hand over to Samuel and Trevor for the presentation.
Okay, thanks so much for the very nice intro, Leo. So yeah, hi everyone. I'm Samuel, and Trevor is also here on the call. I'll be doing most of the presentation, and we'll both be jumping in for the Q&A and the discussion. And today I'm going to present studying the interplay between the actor and critic representations in reinforcement learning, which will be at unclear later this year in Singapore. And so there is a lot. So Trevor and I are first co-author on this work, and there is a lot of very cool people that got involved as well over the course of the project. So Pablo Castro is a professor at Mila and also a researcher at Google DeepMind. Prakash Palangadan is also a professor at Mila and at McGill University. Chris and Stefano are both at the University of Edinburgh as they are professors, assistant professors. And last but not least, Dave is a fellow at the University of Edinburgh and also at Google DeepMind. Yes, so this work is a collaboration between all of us. And I wanted to start this presentation with a little allegory on what is the promise that deep learning has made to us as reinforcement learning researchers and practitioners. And essentially, deep learning makes this promise that you will not need to do any manual feature engineering anymore, because you can have models that extract all the relevant information directly from the raw data. Now, if you work in RL or anywhere close to RL, you know that this is very dependent on your specific use case today, at least, and that feature engineering is still very much alive in many applications of RL. But what's completely undeniable here is that deep learning is a very powerful tool that opens up RL to problems that will not have been tractable before, such as, for example, learning control policies directly from pixels or other types of high-dimensional observations, which is the focus of this work. And to wield this tool effectively, the community has been designing and proposing RL algorithms and model architectures that are becoming increasingly complex, with many components and learning objectives that are jointly optimized. And so it's easy to feel a bit lost in the modern deep reinforcement learning landscape today, with all of the choices you need to make when you are trying to design an RL agent. So in this study, we're going to take an approach that sounds very simple, but can still lead to very powerful insights. And it's to characterize and then quantify what information the model learns to extract from observations. And based on these information point of view, it can help us understand why certain approaches work well or only work under specific conditions. And we see that it then helps us understand and inform design decisions about our architecture, our models, our choice or algorithms, and also the learning objectives we use. So now, taking this information-based point of view would be challenging if we just looked at the model outputs alone. So instead, we make this cut inside the model to uncover these latent features Z, which are being extracted from observations. So you can view everything under the cut in the model as the learn representation, which is this function that maps raw observations to these latent features Z. And why you make the cut in the model is arbitrary. But since we want to understand how the model processes information, it makes sense to make the cut once most of the processing has taken place already. So we make this cut basically by looking as defining as the learn representation all of the layers up to the penultimate layer of the model, and then this last layer represents the policy head, and then we're going to look at the information that is extracted by this mapping between the observation and the latent features, which we call the representation. And we expect this representation to have several properties if it to be effective in as a way to extract the right information for the model. So first, you need to still be able to select the optimal action from these latent features. And you need to be able to do so not just on the data you've seen during training, but also to generalize to observations or parts of the environments you may not have visited during while you were training the agent. And lastly, you do want to be able to compress this information into a compact and structured feature space so that it's easy for the policy head to then map that to the optimal policy. Now, in the paper, we propose a formal definition for this. And broadly speaking, you can view the first two properties I talked about as this first condition of optimality conservation that needs to, you need to be able to still optimize your learning objective under the full distribution, no matter just if it's including both your training and your testing data. But also you have this last property, which maps to the second condition of doing so in a way that you are compressing the features the most possible. Now, in this paper, we look at this class of reinforcement learning algorithms and models that are called actor-critic algorithms that are a bit more complex than the model I just showed now, because they have two components, the actor and the critic. And the actor is optimizing a policy gradient objective, while the critic is learning to predict state values, which are then used as baselines in the policy gradient objective to reduce the variance. And you can imagine two different types of model architecture to learn and optimize the actor and critic. On the left, you could have a shared representation where the actor and critic essentially share the same, learn the same mapping and the same latent features. And on the right, you could imagine this decoupled architecture where the two learning objectives of the actor and critic are optimized completely separately. Now, what has been found in prior work already, and we further highlight in this study, is that the in on-policy actor-critic algorithms such as PPO and others as well, we see that the decoupling approach leads to better performance. And on the right, I'm showing distribution of scores for different algorithms, and the way to read this figure is the x-axis is the score distribution that you get over both the train and test sets, and we define I will define the train test set a bit later, but broadly speaking, the test set will tell you how well the algorithm generalizes, and the train set tells you how performance tells you how sample efficient this agent is given a fixed number of environment interactions. Now, why are decoupled architecture more effective? Well, in prior work, it's mentioned that this performance delta is thanks to having different training dynamics in the actor and critic, such as gradient interferences or different tolerances to using more samples, more epochs over the training data being collected. And in this study, we go a bit further than that and make a stronger claim. So we don't say that these prior claims are wrong. We actually agree with them that the actor and critic do have different training dynamics. But we also say that they have fundamentally different optimal representations. And so even if training dynamics could be perfectly adapted to the actor and the critic in a shared representation, it would still not be a wise choice to share and have a unique representation, because we say in this study that the actor and critic will have different optimal representations that specialize in extracting very different information from their observations. And so that brings me to the first big insight of the study, which is that we observe a clear information specialization in the actor and critic representations once we decouple the actor and critic networks. So to quickly go over like the way we evaluate agents, we study learning control policies from pixels in both discrete and continuous action spaces. And we do that in two benchmarks, so ProgGen and Pixel Brax. And each benchmark has multiple tasks, and each task can have a variety of different environment instances, which we call levels, like video game levels. And on the right, you can see like different possible levels for one of the games in ProgGen. And you can see that each level can have a different background, different number of enemies, or platform layout. So that gives like some variety in terms of the environment that the agent gets to experience. And it also lets us split the environment instances into train and test sets of levels. And that lets us measure, on the one hand, the sample efficiency of the algorithms on their train set, given a fixed number of environment interactions, but also their generalization capabilities to unseen observations and environment variations by measuring them on the test set. So as I mentioned, we also use this benchmark, Pixel Brax, which I'm plugging as well in there because this is something we've released with Trevor a couple of weeks ago. And this is essentially the similar benchmark, a re-implementation of the distracting DeepMind control suite, where you could have like different colors, distractors, and video distractors to act as also these different levels in your tasks, and then split between a train and test set and measure both sample efficiency and generalization capabilities. But we have this added nice thing in PixelBrax that we use the Brax dynamics engine, and that lets you run experiments up to 100 times faster than in the original benchmark. So make sure you save this link if you want to run these sort of experiments and speed up your training. Okay, plug over. So and as I mentioned before, we are going to study on-policy actor-critic algorithms. And in this case, we study non-recurrent model architectures. But the approach we take can be easily extended to off-policy algorithms, offline algorithms, and different kinds of architectures. So the way we going to evaluate these learned representations is by measuring different kinds of mutual information-based metrics that quantify different information types that the agent is extracting from the environment. So this first quantity of information is the level information, IZL, which measures how much information is contained about the identity of the training levels in the latent features. So in other words, it tells you how easy it is to identify the level you are in from just having access to the latent feature. Now, there are direct connections between this metric and how overfit the representation is to the training levels, and also to, by extension, the amount of generalization error you're going to get between your train and your test performance. The second quantity we look at is the information between Z and the state values. And then we have two metrics that measure information that the agents extract about environment dynamics. The first one tells you how easy it is to identify what action was taken if you have access to the latents obtained from the current observation and the next time step observation. And the second metric tells you how easy it is to identify a pair of latents coming from consecutive observations and non-consecutive observations. And this can be viewed as the first one is to extract information that are related to action and the inverse dynamics of the environment. And the second is about the next states and future state transitions. Now, I'm going to share the change of information extracted that we see between when you start from a shared PPO model architecture and you compare it to a decoupled PPO model architecture. And the first thing we see is that the actor representations become less overfit to their training environments, while the critic representation becomes more overfit to the training levels, which is expected since you do tend to perform a lot more gradient updates to feed the critic than to feed the actor. So the critic sees has a lot more opportunity to extract and learn to extract this sort of information and overfit. But there are also theoretical arguments that tells us that the critic generally needs more level-specific information to reach optimality on the training set. And we discussed this theoretical argument in the paper in detail. Now, the second specialization we see is this time both the actor and the critic are increasing the information they get about values, which is quite surprising for the actor because it's not doing any sort of value prediction anymore once it's decoupled. So we'll get into that later. And in the last two metric, what we see is that there is an opposite specialization. So the actor focuses on extracting information about the action selection, while the critic looks at next step dynamics. And we also discuss theoretical implications of this in the paper. For the sake of brevity here, I'm going to skip those, but the key insights that to really look at here is that in 3 out of 4 metrics, the actor and critic are taking opposite roads to information specialization. And you can see that they are clearly becoming specialists in different quantities. Now, this specialization correlates well to having better performance, as I mentioned earlier. But something that you could wonder is that maybe there is a shared reason, shared co-founder why results improve and specialization happens. And it's true that once you decouple the model, you have twice as many parameters. So maybe like just the larger model is what enables this specialization and it's like higher returns. So just to check this, sorry, I forgot to update the figure on the last slide. So this is the right figure to look at on the left. But just to check this, we also try to scale up the different model sizes that you see in, so for the shared and the decoupled models. And what we see is that actually it's quite surprising here, because even if you double or quadruple the number of parameters in the shared model, you get nowhere close to the performance you get on the decoupled model. So it's actually more parameter efficient to decouple your model than to try to make your model bigger. So if you are restricted in the number of parameters you can use, try to split your model in two, which is kind of counterintuitive, but it works. Now, let's go into this second insight, which is that now that we established that the actor and the critic do specialize, to try to identify what matters for the actor here. So there is an inherent contradiction with the role value distillation plays into the actor's representation, and whether this is actually beneficial for the actor representations or not. And that will become apparent in a minute. So PPO, which when it uses a shared architecture, is jointly training the representation under both this policy gradient and value prediction objective. So from a representation learning perspective, PPO with a shared architecture is doing some value distillation every time it updates the critic. Now, when you have a decoupled architecture, you do much better, but you do that by not doing any value distillation on the actor. But these other algorithms, whether they are coupled or decoupled, they actually do a lot of value distillation updates, and I will explain them in a second. But in fact, they do 4 times as many value distillation updates than shared architecture PPO. So why does value distillation work so well in this case? So let's visit how PPG and DCPG perform value distillation first. So they have this decoupled architecture, and they add an extra head to the actor latent features. This auxiliary value head, which is updated as follows. So this value head is only used to distill value information into the actor's representation. And it does that by accumulating all of the last n PPO. So all of the data that was collected during the rollout phases of the last n PPO update phases into this big buffer called box. And then it samples from this buffer to perform a lot of value distillation updates into the actor's representation. And the loss is very much the value prediction loss, right? But over this much larger batch of data. And there is also this behavioral cloning term to make sure the policy doesn't deviate too much from the how the policy was before you started this distillation phase. And for those who are wondering, in terms of like when you use a shared representation in PPG or DCPG, it's actually the original PPO architecture, but you are using a stop gradient operation to not update gradients, to only basically propagate gradient through the actor's representation when you are in this auxiliary phase, and not when you are in the PPO phase when you have a smaller batch of data. But so the common thing here, whether you use a shared or decoupled architecture, is that you only update the actor representation with value distillation with much larger and diverse batches of data. And we wanted to validate that this is actually what drives like the performance increase in these algorithms. And so what we did is like we fixed the number of value distillation updates that you do on the actor, and instead we make the box smaller. So we force like updates to occur over smaller, a less diverse set of data. So you see a lot more of the same transitions, basically. And clearly here, you can see that when you start from 32 times, you have good performance, right? The auxiliary batch size. But once you reduce this auxiliary batch size to towards 1, so to be basically the same thing you do when you expect the critic in regular PPO, you lose all of these performance gains that you gained before. So it clearly matters to have this diversity in the training batches. And if we look at two of the metrics we discussed before, so the metric that measures overfitting and the metric that measures information about the value function, you can see a very interesting trend as well, which is that most of the increase in IZL happens irrespective of the auxiliary buffer size, and is mainly driven by performing additional gradient updates on the network. Because most of this increase happens when you have a single, like the batch size being as small as in PPO. On the other hand, the value information only increases once data diversity is high enough. And if we take this information extraction perspective, we can actually think of representation learning, any kind of representation learning, as increasing or decreasing the mutual information between the features Z and some quantity Y. So in this case, Y will be like the value, the set values. Now we can decompose IZY into this level dependent and level invariant components, which this first component is the information about Y that exists irrespective of like which individual training level you are in. And the second part is the information about Y that is specific to individual training levels. So to give an actual example, concrete example of this is if you have this example level in Coin Run, which is one of the games that we train in. You have this agent, the little blue guy. He needs to reach the gold coin at the right of the screen, and he will get a reward if he does that. But if it gets touched by an enemy, he will die and not get any reward. And what the agent actually sees at this current time step is just what is in the purple screen here. And so if you think about the information about the value function, if the agent uses the information that there is this enemy nearby to reduce its estimate of the value, the state value, it's using level invariant information because it just uses the fact that enemies have a chance of killing the agent and preventing it from achieving any reward. And so it should reduce its estimate. And that applies regardless of the level you are in. But if instead it uses the background of the level to be able to infer that it is in this specific training level, and then predict how many time steps it will take to reach the coin at the right, to predict the value accurately, then it's exploiting level-specific information about the value function. And so to go back in this split between invariant information and dependent information, it's actually hard to measure these components individually. But what we can see is that IZV is increasing. IZV is increasing when the data is very diverse, but at the same time, IZL is stopping to increase. So the level dependent information stops to increase, and then that means that like at very high diversity in the batch size, the increase in value information is driven by an increase in the level invariant information instead. And that coincides with better agent performance as well. So it comes down to this insight. When you perform value distillation, you should do it over diverse data for the actor, because the actor it's very important for the actor to learn to capture level invariant information. And what is even more interesting here is that it doesn't matter if you do value distillation or any kind of other types of predictions about the environment. At least in our experiments, like we tried many different types of representation learning objectives. And when we do an objective that's based on identifying the dynamics of the environment, so basically it comes down to predicting whether like an given state transition actually came from the environment or is a fake state transition. We see that it's also whether or not this improves the actor representation is dependent on whether you are using a diverse batch of data or not. And on the other hand, data augmentation, which is always increasing the diversity of the training data, works no matter what algorithm you test it in, because it's consistently increasing the data diversity. So you are guaranteed to get at least some improvement in performance. So in short, like it's more important to have an objective that encourages the actor representation to capture level invariant information in general as an inductive bias, instead of like thinking of what specific quantity Y you want to capture information about. And so I'm going to finish the presentation with a short third insight that we also found that also were quite surprising to us. And it's that, if you recall, like when we looked at the specialization of the PPO agent, we saw this very high increase in information about the value function in the actor representation in decoupled PPO, which, if you recall, there is no value distillation taking place here. So why is IZV increasing when no value distillation is taking place? And what we found is that the critic actually influences data collection throughout training, as we see that there is a clear increase in the value information that is contained in the observations that are collected by the agent policy. And we see also that, like, if we try different representation learning objectives, such as MICO, which relies even more on value information to be optimized, and dynamics prediction, which instead relies on like this action and other dynamics prediction, we see that this also consistently increases the whatever information is contained in the observations that the agent will collect. So the critic is able to influence the policy updates in a way that it biases the policy to collect data that will help the critic's objective, even when you fully decouple the actor and the critic network. So there is still this interaction and interplay that exists because of the training data, and that because they are trained on the same training data which are collected with the agent policy. So just to summarize this, like 3 takeaways that we presented here. So do the actor and critic representation specialize in the information that they extract? Yes. How can we further improve the representation of the actor and critic? So for the actor, it's really important to promote extracting level invariant information. And does an interplay still exist between the actor and critic once you decouple their respective models? And yes, because the critic is able to influence the actor policies to collect data that helps optimizes the critic's learning objective. So I only focus on 3 insights in the paper, which I think are the 3 most important insights. But there are a lot of other things we talk about, which I would leave to either for the discussion or just to check out in the paper directly. So maybe I will leave it on that slide, and we can start like with questions and discussion. And if you want to like discuss these points or any other thing that like came to you during the presentation, be very happy, Trevor and I, to answer your questions. Thank you very much.
Thank you, Sam. That's a really interesting talk. I will stop the recording now so that people can like ask questions freely, and you won't be on YouTube if you ask questions or turn on the camera. And